Thank you so much. Welcome, everybody. I would like to ask you 3 questions. The first one, what would you do if there is no water to shower? What will you do if you're an operator and there's no water to cool your reactors? Or what would you do if you're a farmer and there's no water to cultivate your vegetables? These 3 questions point out that we need to look into the cyber security aspects of our water distribution networks, since water is a crucial aspect of human existence. But first, let me introduce myself. My name is Rosanne Aartman, and I'm a master's student in System and Control at the Technical University of Delft, and currently doing my graduation thesis on cyber attack detection in water distribution networks, and doing so in collaboration with Batenburg Magion, which is a company that specializes in industrial automation and industrial cybersecurity. Now, within the Delft Center of System and Control at the Technical University of Delft, we are designing controllers for real dynamical systems. However, these dynamical systems are often exposed to faults, which can lead to failures. Therefore, the Fault Tolerant Control Research Group designs anomaly detectors and fault tolerant control systems so we can operate safely. Now, these anomaly detectors can also be used to detect malicious cyber attacks in our industrial automations, and therefore becoming the union of my thesis project. And today, with this presentation, I aim to explore the current landscape of cyber-physical attack detection methods within water distribution networks. Well, these are the things I will be covering today. I will first explain something about what a water distribution network is, what cyber attacks are. Well, I hope all of you are known with that. Some model-based approaches, some data-driven approaches. Then I will tell you about stealthy attacks, and at last, watermarking. So our water distribution network is a distributed control problem. We first have our consumer network containing households and the industry. We have a primary control layer having local control systems at multiple locations, each delivering water to our consumers. The primary control layer is connected via a communication layer to our secondary control layer, which is the centralized control system. The local control system sends its measured data to the centralized control system, and the centralized control system sending control inputs, for example, as turning pumps on or turning pumps off, or closing or opening valves. Now let's zoom in on a specific local control system. This consists of the physical system containing pipes, reservoirs, some sensors, which could be pressure sensors, flow sensors, or level indicators. And then we have actuators, which in the case of water distribution networks are pumps and motor-controlled valves. Now, within the local control system, there is also a local controller. In this case, making sure that if the level of the water in the reservoir gets too low, the pumps will shut off, because we do not want our pump to be pumping air, because it's not made to pump air. It's made to pump fluid. However, in these cases I'm going to show you today, the local controller is being left out. We are more interested in our centralized control system. because the local control system and the centralized control system are often at different locations. So, for example, the local control system is located in Amsterdam, and the centralized control system could be located in Rotterdam. Therefore, the communication has to go via a network. Now, what makes a distributed control system so vulnerable to cyber attacks? It is the point of the network. So, some attacks that could happen are man-in-the-middle attacks, rerouting attacks, which can lead to false data injections or replay attacks. Now I'm going to give you some examples of what consequences these effects can have on our physical system. This could be an empty reservoir when there's a high demand of water, water overflow. We know water is a scarce product, so we do not want to waste water. Or letting a pump with no air in it and then leading to a pump outage. So we are within the world right now very eager to have industrial automation. We want to automate everything. However, this comes with consequences of being exposed. And together with the increasing water demand and additionally, unfortunately, the human-made climate change, making the water distribution networks a target for cyber-physical attacks. So how can we detect these cyber-physical attacks in our critical infrastructure? When looking to this problem with a controlled theoretic approach, we can use the dynamics of our physical system to design the anomaly detectors. And two approaches that are very distinctive are the model-based approach and the data-driven approach. With the model-based approach, we are using a mathematical model to represent the nominal behavior of our physical system. Over here, we have an estimator using to estimate the expected behavior of our dynamical system. We use the control input and the sensor output to create our estimation y tilde. When comparing the sensor values with our estimated output, we are computing a residual. I need to point out the estimator is not capable of reproducing a 100% accurate estimation. So therefore, we will always have a residual. And additionally, we know sensors are not precise as well. We would also have some measurement noise. So therefore, we have to perform some statistical analysis on our residual. And if we do so, we can have a detection. Now, some pros of our model-based methods is that we can detect unseen anomalies. And one of the main pros is that this estimation is computed based on the laws of physics. However, to do so, we need an accurate representative model of our dynamical system. But to create one, we have to induce simplifications and assumptions. Now on to the data-driven methods. These methods are often machine learning based. And within machine learning, there is made a distinction between supervised learning and unsupervised learning, where with supervised learning, we need labeled data. And in these cases, we need data which represents nominal behavior or anominal behavior. And then we have to have a labeled, for example, this is a faulty behavior where our tank is overflowing, or we have behavior where we have an empty tank. Now I'm going to explain to you two commonly used approaches. However, there are many, many more methods that are proposed within research. I have to say, I'm trying to explain these methods to you. If you have any questions after, please come to me and we can talk about it further. So a convolutional neural network, for those of you who have been to a previous presentation here, might already have heard some explanation. With a convolutional neural network, we first take the convolution. So we have a small block which is moving over our image, and then we're trying to specify certain parts of our picture. For example, the eyes and the nose of a bird are very specific. Then we can use those specifics with a lot of labeled data, for example, again with pictures of dogs or cats or birds, which can learn what is the shape of the nose of the bird or the shape of the nose of a cat. And then, because we have learned the parameters, it can eventually say we have a high chance that this picture is a picture of a bird, and we have a low chance this is a picture of a dog, since the shape of the nose is not the same as we would expect. So now I have explained this as part of an image, but in my case I'm looking at a water distribution network with a lot of input data representing a complex infrastructure. So let me give you an example of how a convolutional neural network could be used to identify correlations and dependencies of system parameters. So say, for example, we have these 5 parameters. By feeding a lot of the input data, our neural network can learn this pattern and the certain effects that, for example, A has on B. But now the good question is, how can we use this to perform anomaly detection? So say, for example, I impose a delta on my parameter C. My network knows what the correlation is of B to C, D to C, and E to B and D. So when I have an adjustment on parameter C, I would expect to see the impact I know on B and D. However, this is not the case. So therefore, we have an anomaly at C. So this was quite a mouthful. So I am going to take a sip of water, and you guys can let the things I said to you sink in. So now we move on to autoencoders. Well, first I will try to explain this with a picture. Our input is this toad, 3D toad, and we have an encoder trying to compress the dimensions of this input signal by learning the parameters of our encoder function. Then we have in the bottleneck a lone dimension of our input, and then the decoder tries to reconstruct our input by having its own function and its own specific parameters. And then again, having a reconstruction of our mushroom. But I hear you say, these are not exactly the same. But are we happy with it? I at least am, because I can see this is a mushroom with a red head and the white circles. Quite good. Well, an autoencoder can learn the parameters of the encoder and the decoder by using a lot of data and having the objective of minimizing the reconstruction error. So now moving on from this picture to the water distribution network. So say, for example, we have a certain function. Our autoencoder knows when having certain input signals, it can reconstruct the points on this nonlinear function. So say, for example, we have an anomaly, this red circle above. Now our autoencoder is going to try to reconstruct this point onto its own function. Then we will have the dot at the left. But now we have a very high reconstruction error, letting us know we have an anomaly. So I hope that I've been able to show you 2 examples of data-driven approaches. The pros of these methods are it can be used to learn complex nonlinear structures, that are water distribution networks, and they do not need process knowledge for that. However, they do need a large amount of data to do so, and it's a highly computational, complex problem. So now we have, as a society, developed a lot of good methods to detect anomalies. However, the adversary has its fancy self as well, and is able to inject a stealthy attack by following the expected behavior of our system, by, for example, mimicking noise or exploiting the control theoretic properties. And with that, our closed-loop control system becomes an open-loop system. And therefore, this can have divergence in our system and catastrophic effects. So these stealthy attacks are quite risky. So what can be done to detect these stealthy attacks? Well, the previous two methods are actually very passive, and we can do something actively to increase the integrity of our signals. And this can be done by implying a watermark. For example, on the left, you see a watermark over a picture, which some of you might have been using in the past. This is a static watermark, but we can also apply a dynamic watermark over, for example, an audible signal. By having a lower power spectral density, we can imply an inaudible watermark over our signal. And the thing is, we know what our watermark is, but the adversary does not know what our watermark is. And to be more protective, we could also change this watermark over time. Now, within this local control system, we can apply additive watermarking to our control input. This could be with Gaussian noise before sending it over the network to our local system. However, this can have effects on the performance of our local system. So therefore, we can also use multiplicative watermarking by imposing a filter on the sensor values before sending it over the network. And then on the controller side, we use the inverse of our filter and having it fed to the anomaly detector. And research have shown that this can lead to anomaly detection. So with this presentation, I hope I've shown you some control theoretic approaches to a OT security problem. And I think that we should still develop methods to be able to detect stealthy attacks and thereby increasing our resilience and making sure that we still have water in the future to shower. The operator has water to cool his reactors, and the farmer has water to cultivate his vegetables. And I'm very curious, what method would you use to apply for anomaly detection within water distribution networks or other industrial control problems? And with that, I would like to thank you a lot for your attention. Does anybody have a question? Yeah. Oh, yeah, I will. The question was, what other applications do you think these anomaly detection methods can have? Well, for example, my professor is also researching in wind farms design. So we want to have the communication between our wind turbines to be safe. Another example could be the cars that are platooning. So you have a leading car and then cars behind it. They are sending their data to each other, so you want that to be safe. Does that answer your question? Well, thank you then for your attention.